All right, so we're having a discussion a little bit, go through some terms of what remote sensing is, different types of sensors, and then try to show you how some of this applies to agriculture, some of the sensors that are available, some of the terminology. I took a remote sensing course in college from this guy, Dr. Campbell. Here's his definition of remote sensing. It is the practice of deriving information about the Earth's land and water surfaces using images acquired from an overhead perspective using electromagnetic radiation in, on, or more regions of the electromagnetic spectrum reflected or emitted from the Earth's surface, also known as taking pictures. So there is a difference between what we call direct versus remote sensing. Remote is remotely. So when you take a soil sample, that's a direct sample to get a nutrient content. If you take a tissue sample, that's direct sampling to figure out what's going on with the crop. A Varus machine that runs electric current through the soil, that's direct sampling. When you take a photograph from a distance, that's remotely. When you use green seeker, that's remotely. You're not touching the crop, you're getting a signal from a distance. Another good term to understand is when we talk about passive versus active sensors. Most of the time in agriculture, we're going to be using passive sensors. Something that is not emitting light itself, it's accepting it. So a camera is a passive sensor because sunlight, the sun, creates the wavelengths that we use to measure. They're reflected off the Earth's surface and we use the camera as a sensor to collect it. Green seeker is different. It's an active sensor. It creates the signal. It creates the wavelengths that bounce off the crop and come back. That's why green seeker doesn't have to rely on sunlight, because it creates its own signal. So that's an active sensor. Most of the sensors that I use in a drone or we put in planes, a lot of those are just passive sensors. So the electromagnetic spectrum, it is important to understand some of these parts because of the different things that are being sold and used in ag to understand where these wavelengths are and how they relate to each other and how they're used in these different sensors. If you start all the way over here with our longest wavelengths, we have the radio waves. Radio waves are what we use in radar. Radio detecting and ranging, that's what radar means. The next one up are the microwaves. Where microwave is close to radio, you can also use microwaves for radar. We can use it for imaging. In satellites, they use it to measure parts of the atmosphere, and we can also use it to make thermal or heat measurements. Where microwave bumps up against infrared, they also overlap. Infrared can be used for thermal. When you're on this end, this is the far infrared, and that's used for thermal. When you get to this point, this is near infrared. If you notice your visible spectrum right here, here's the red light. Infrared is on this side of red. Ultraviolet is on this side of violet. That's what they mean. Infrared, the wavelengths right above red. Ultraviolet, the wavelengths right next to violet. So the infrared spectrum is close enough to the visible spectrum that we can also use it to see. Use it to look at crops as an image. We can't see the infrared spectrum, but we can use cameras to see the infrared spectrum. It is reflected off of a plant. So far infrared is further away from the visible light. We can use it for heat. So a lot of our thermal cameras use far infrared. But the near infrared is what we use a lot to do NDVI type measurements. So here's the visible spectrum, a very small sliver of what we can see reflected off of plants. When you get to ultraviolet, you see I put a star right here next to visible. This is the one we use the most. This is the one we use most for crop monitoring. This and near infrared are what we're going to use. Satellites do use some of these. Ultraviolet is scattered by the atmosphere. We can't use it. X-rays are used for X-rays, and the only use I know for gamma rays was to create the Hulk. So we can use radio waves in ag. We don't necessarily use it for crop monitoring, but ground-penetrating radar can give you similar information to a Varus. It sends radar down through the soil, and this is something from the NRCS. It sends radar through the soil, and it can measure different soil horizons. And the reason this would be important for crop monitoring, this is a project we did almost 20 years ago in Virginia. These 4 different soils that were done by an Order 1 soil survey, a very dense survey, if you could map that with ground-penetrating radar or a Varus and get these horizons better, you see this bojack right here was getting about 85 bushels of corn. Well, it had 3.6 inches of water for every 4 feet. The Wickham 3, with 160 bushels of corn, held 7 inches of water for every 4 feet. So if you can use something like ground-penetrating radar or a VARIS to get more accurate maps of the soil horizons beneath your feet, you can actually use this type of sensing to get a better idea of why there might be differences across that field. What's the difference in the soils? Because your soil maps are accurate at a certain scale, but if you're really trying to dive into why some parts of the field might perform better than others, it could very well be the water holding capacity of those subsurface horizons. There might be higher clay, and that's what's going on. The subsurface of these soils have a bit higher clay. So the far infrared are closer to microwaves. We use them for thermal images. We can use them to look at where things are warmer or cooler in the fields. What that could be used for is within crops that use evapotranspiration. We can use thermal images to measure how well some plants are doing. Some thermal images have been used to measure pesticide resistance in weeds. Because if you spray Palmer glyphosate and it survives, it keeps transpiring and you can measure it versus a plant that died. So thermal imaging can be used in crops. It's used a lot in irrigation systems for research. But more of what we end up dealing with is that near-infrared spectrum, the one that's close to the visible spectrum. It's reflected by plants. Now, we can't see it. So where it's close to the visible spectrum, it's reflected by plants. We can use it in film and photography. When someone shows you an NIR image like this, and this is an NIR band, that's not the color of NIR. They've colored the photograph. We can't see it. So they've assigned values. You could assign colors to this in a computer. So if someone shows you an NIR, don't think, oh, NIR is black and white. It's not. It's the plant reflects it. We can't see it, but we can use cameras to see it. So here's the same exact spot with a visible spectrum. So because different plants will reflect different amounts of NIR depending on their health, we can actually start to do a comparison between these two spectrums to get an idea of what the plants are doing, what we can't see. So one of the first types of photographs, has anyone ever looked at a color infrared photo before? Yeah, so color infrared photography was something we could use from planes and satellites. It used the NIR band. It also had blue and green. That's why it's color infrared, the color light we see plus the near infrared band. So this is actually Ocean City. I grabbed this online from Landsat 8, one of our satellites. Here's Route 90. Here's OC. So blue and black are often roads and water, so this is a good image to get an idea of everything you can see. White, green, and tan, soil and buildings. So we can see the buildings here. We can see bare fields. Light pink, less vegetation. Red, thick vegetation. So of course it would depend on when this image was taken, what time of the year. But from a distance, now you'll see with drones and with some of the other cameras we have, we can get a lot more detail. But initially these kind of images were great for getting an idea of what's going on across a region. Of course, it's going to be expensive to try to collect an image like this every day. So it's more something people might use once a year, once every 3 years to get an idea of what's going on in the region. So you monitor crops this way over a longer period of time. And we'll talk about spatial versus temporal scales in collecting this kind of data. The National Agricultural Imagery Program, it's a federal program. You can download and look at these images for free. This is the Carvel Research Station where I work, so you can see and look across all these crops. They collect it every 3 years. It has a 1 meter resolution. It's a pretty good resolution. It's not something you're going to use in season to monitor, but you can go back through time to see what was in this field at a certain time, how healthy might some of things looked. Again, this is something that's a little more useful for people that are looking at larger scale. Maybe they're trying to figure out what crops are grown in a certain region across the planet, across an area, across a county, how have things changed? Can we get an idea of how much corn was grown in this year? That's what this imagery can be used for. It's not something you'll use during the season, but it is free because it comes from the federal government. And of course, because it's the federal government, the names of these programs change. This is currently the name of it. All right, so then we get into the visible spectrum, or not. So the visible spectrum is using cameras. So the first remote sensing that would have been done was about 1850. When we had hot air balloons and we had cameras, people went up and started taking pictures of the landscape. In 1909, we started using airplanes. Of course, a lot of that for in World War I and II, spy photographs. So these are all images from the same farm using an airplane. Satellites in the 70s started taking pictures from a distance, and these are images we've taken of these same fields with the UAV in the last year. So an airplane is great for getting images at a better scale. Of course, you have to pay to fly that airplane. You're not going to send it up every day versus a cheaper UAV. Satellite imagery is great for getting a larger scale image, a wider region, but it's not necessarily going to be at a very good resolution. So the wavelengths that we use for cameras, even though we talked about the whole electromagnetic spectrum, we really focus on the visible wavelengths and near infrared. Because if you look at what penetrates the Earth's atmosphere, that the ones that we can use, the visible penetrates, so it reflects off the surface of plants and we can measure, and the infrared, the near infrared, penetrates the Earth's atmosphere, so we can use these. So these are the ones you should probably be familiar with when you're looking at the technology that is coming, the cameras that are coming, the information that's going to be available. Most of it is going to use these kind of wavelengths. Now, radio waves do penetrate, but it's probably not something that we're going to use much to measure crops. So most of the cameras you have a filter on them to remove the near infrared spectrum because it can cause issues or haziness within your images. You can take a camera like this one, you can buy one off the shelf, remove the IR filter, end up with an image just like that to see the near infrared spectrum. You can do that. So your cell phone, your consumer cameras, they're all going to have filters to remove that infrared light so it doesn't mess with your image. So one of the earlier issues they had with trying to fly drones is we didn't have cameras with multiple lenses on them. So you would have to fly it once with the filter removed, and then once again with a camera that has a visible spectrum and have two images. As you'll see now, we have cameras that have multiple lenses on them with different filters so that when you fly over one time, you get all of those wavelengths and we can start to do some of this analysis. So a multispectral camera is one that looks at several spectrums at once. It's going to have several different lenses on it. And you can select, you see there's a whole range of wavelengths. We can focus in on a small set of wavelengths, or we can select a wider range of wavelengths so that we can start to look at these different reflections that plants are doing with these wavelengths across the area. So here's one that would have blue and red. It can specifically look at the blue band, the red band, and then the near infrared band. And the sunlight's reflected off. It's a passive sensor, collects all that data in one flight, and then we can look at all these images and start to do some of these calculations that we're doing. So plants, what somebody figured out, a scientist at NASA, when they started sending these satellites up, he was looking at, they have multispectral cameras on satellites. And he wanted to figure out, can we use all these wavelengths to at least measure plant biomass across the planet? So a healthy plant, it reflects green light because you can see it. When you see green, that's what's being reflected, and it's absorbing not necessarily all the red light, but it's absorbing red and blue, and that's why you don't see blue when you look at a green plant. It's reflecting a lot of the near-infrared band. A lot has to do with the cell walls. Now you can't see the near-infrared band, so it's not reflected back at you. It doesn't mess with your eyesight. As you get to a stressed plant, it starts reflecting equal amounts of green and near-infrared. Again, you can't see near-infrared, but if we have a camera that can, now we can start to do a difference between these areas. When you have dead plants, they reflect everything similar, all of the different light. So if you have healthy plants and we can measure near-infrared with a camera and we can measure the green, then we start to figure out what kind of calculations can we do to measure biomass. And that's where we came up with NDVI. Well, I didn't come up with it. A scientist at NASA came up with NDVI, and I'll show you there's several other indexes. These are obvious satellite passes from Landsat. He looked at all these bands they were getting, did different calculations, and found that this was one of the best for measuring biomass. People will tell you that it measures plant health. It can't really tell health. It can tell biomass So you could have a very healthy plant by itself in the middle of a field and nothing else around it, and we'll have a low NDVI reading because it's a plant by itself. So it's more of a biomass measurement. So NDVI stands for Normalized Difference Vegetation Index. He figured out that if you took the NIR band, subtracted the red, and divided it by NIR plus red, you get a scale. It goes negative, but in most cases my numbers come out to about between 0 and 1. And if you're, as you're up near 1, you have a lot of reflectance, you have a lot of biomass. Those values get below about 0.5, you're starting to see a stressed area. So there are other indexes. I want to make you aware of this because you hear NDVI said a lot, and NDRE and a couple others. But most of the ones that people are measuring are either true NDVI or false NDVI. But there are a lot of ratios. I have a paper that has a list of probably about 50 different ratios people have come up with. There's a simple ratio where they divide NIR by red. They have a soil adjusted to look out for soil reflectance. The visible atmospheric resistance doesn't need NIR. It's green minus red divided by green plus red plus blue. Some people call this false NDVI. You don't need an NIR camera. It works okay in most cases, but it's not as good as if you have that NIR band. It does work okay. And then there's green NDVI and GDVI and GoSavvy, and there are very specific ones that people have figured out to look at a very specific wavelength. Some of these companies that are selling cameras for drones will let you select the wavelengths you want. In most cases, it's cheaper just to get the one that comes with the bands you need. But just be aware that there are more indexes than NDVI. It's just NDVI is the easiest one for us to use, and it works very well in most cases. There are also hyperspectral cameras. Now, hyperspectral cameras, instead of focusing in on one wavelength, they get a whole range of the electromagnetic spectrum, and they get it in small increments. It produces a lot of data. But what they've actually been able to find with these types of cameras is, you can see this is done out in the desert, antelope bush, Jeffrey, grouse, sedge, that these plants reflect at different portions on that spectrum, different amounts, different wavelengths of these lights at different amounts. So we can start to separate out plants. So while NDVI is great for measuring biomass, some of these claims that we're going to be able to tell you what weed is in that field or what plant is there or these different soil types, NDVI is not going to be as good at that as hyperspectral. However, some of the cameras I've looked at are like $20,000, so I won't be buying one anytime soon. It can also separate out different soil minerals. So it's possible what we'll see in the future if they make these cameras cheaper, that this is the kind of technology that might actually help us ID weeds in the field, maybe, or look at different plant types. But right now, you would have to be more of an expert. You're still going to have to walk out in that field and scout and see what's going on. These cameras are not quite available on the consumer range as something you can afford. There's another piece of technology we can use called LIDAR. So just like radar, LIDAR is light detection and ranging. So in the past, we could make topographic maps and what we call digital elevation models from stereoscopy, where they take 2 images from an airplane and they draw out these contour lines, and then they create a topo map and then a DEM. But now we can pretty much stick lasers on planes, fly them over the top, and get a very accurate measure of elevation. Now, while this might not apply to crop monitoring, this is the Delmarva region, and you can see all these different Delmarva bays in this area. So LIDAR can get very specific elevations, and this is where it can come in useful. This is the area around Princess Anne. So here's your visual image, and you can see quite a bit. You can see the different fields, you can see the towns, you can see the roads and the forests, and it gives you an idea of what's going on. Then you pull in a LIDAR image, which is currently for free. If you're in the state of Maryland, you can get all of this information for free. ArcGIS Online for Maryland, you can pull it off of there, and I'll show you another site you can get it from. When you pull in the LIDAR that's getting you elevation, and I'm a soil scientist, so I love this stuff, the white is a higher elevation, the darker it gets is lower elevation. If you look at this line right here, you can see a shelf of a high elevation. This is telling you something that went on in this region. When sediments were being deposited down around Princess Anne, this is Somerset County. If you're not familiar with the area, this is probably about, well, we're in Ocean City, say about 40 minutes away. 40 minutes away towards Princess Anne as you go towards the bay. So now, if you're a crop consultant in this region and you're working with these farmers, now you can kind of see very accurately, if they have fields on these boundaries, why maybe this one's a little better drained than the next one. And right here, what you see, look at this edge. We have this edge of a higher elevation, like a Delmarva Bay coming in here. When you come over to this field, if you look all around this region, where did they put their fields? In the higher elevation portion. And where is the forest? Now, if you've lived there for 50 years, maybe you already knew the landscape. But if you're new to the region, what elevation can get you, it can explain why. Sometimes people don't know why their grandfather has a field in one spot and left trees in the other. When I tell a lot of people that are talking about buying land in the area, I think if that's been under forest for 50 years, somebody probably had a reason to leave it that way. If somebody's not farming it, there's a good chance that it's land that was hard to farm in the first place. So while this doesn't monitor crops, just like that, the ground penetrating radar, you start to get an image of why something might be somewhere in the landscape and how that might help you work with different people in the area of why one field might be doing better than another. Why is one field better drained than another? Now you can tell these people, you've got some kind of old relic information out here that's an upland position right around that. And you can also, right in here, you could find this stream. You could see it if you looked really hard, but LIDAR, which is looking at depths and elevations, picks it out really well. Now you can follow it all the way up through the landscape. It'd be a lot harder right here when you get into this forest, but now you can see where all those branches go.
Does that penetrate in the water or not?
It should be able to penetrate so far, but I don't know how deep. But if it's telling you it's that dark and deep, then yes, it's penetrating the water. I'm not actually sure how far down it can go. So how do we obtain all this remotely sensed data? How can you get a hold of some of it? Some of this stuff's going to be free. What you're going to find out with free things, as usual, is they're not very high quality. We have used planes, and we've used planes for research to get color infrared photos. Satellites, the government's put up satellites. You can get free information from them. You can pay a lot of money for some very good satellite data. Drones, where we're going, I do think drones are one of the easier ways for you to get remotely sensed data. And then, of course, again, GreenSeeker is remotely sensed data. If you're using GreenSeeker or you have a handheld GreenSeeker, you can gather it that way. Most of the satellites we put up there have multiple bands. This is Landsat 8, our most recent Landsat that we have up there. It has blue, green, red, near-infrared, shortwave infrared. Looks at moisture content of soil and vegetation, panchromatic. So when they put up these satellites, they have several bands that they can do calculations and get images to you. The problem with satellite data is getting a hold of it. Most of you aren't going to go out and buy satellite data. You're going to get it secondhand. So there is commercial satellite imagery that the government doesn't do. A lot of it is a lot higher resolution, Iconos, GeoEye, RapidEye, Spot. Planet Labs has about 200 satellites. And if you get satellite imagery from some company, often it's being sold to them by one of these satellite companies. And then we have government and ag companies can purchase the data from them. So perhaps when you're getting something from Instructor or Climate Field View, they're getting it from these companies themselves. And then you can get free government, Landsat 8 or ESA Sentinel, that's a European agency. You can get free data. You'll see it's not always what you were looking for. When you're looking at, if you're going to think about getting satellite data, if you want satellite imagery, one of the first questions you should ask is, what is the temporal resolution? That means in time. So I showed you that NAIP data, which comes every 3 years. That's not enough for crop monitoring. You want something that comes over pretty often so you can monitor the crops without walking out in the field. And then spatial becomes very important, especially in our region when we don't necessarily have 1,000-acre fields. How fine is the scale? Is one pixel 15 feet or 9 inches? A lot of times when I fly a drone, I can actually have every pixel being 1 to 4 inches, which is excellent resolution, but you have to fly the drone yourself. RapidEye, every pixel that you see is 16 feet. That's pretty good. By the time you get up to Landsat 8, you're talking about 98 feet for a pixel. Good enough to get an idea of what's going on, and this is the free stuff in most cases, but it's not necessarily going to tell you across 98 feet if you're trying to get a very high spatial scale of what's going on. A general measurement of the region, fine, but crop monitoring, no. So this kind of stuff, and what you'll see from what Google Earth uses, they pay for the higher quality images. So here's one of our research plots. So Landsat is not going to provide me the data to do research plots. They're too small. Here's one of our research plots. You can see all our tiny little plots in here. If you had 30-meter resolution, that's about 98 feet, that would take up a whole chunk of my plots. You have a couple 100-acre field, might be perfectly fine. Maybe across that field you can see some variation, but I'm not going to see it. You get down to 5, still that's the size of one of my plots. 3.5 is about a half a plot. Even at 1.5 meters, which is about 5 feet, I'm only seeing a little section of the plot. So I could use it, but this is why for us in research, we're a little more excited about drones, because now over this plot, I can fly it, get some information and use it. But if you're on a farm, maybe some of the satellite data over 100 acres is perfectly fine. So you get what you pay for. Google Earth is going to pay for some high quality stuff. Here's Google Earth. They can get stuff that ranges from 50 feet to half a foot. This is the exact same place. Here's where I work, the Carville Research Center. Here's Landsat. Here's Google Earth. That's what it looks like. This is free. I know people like free stuff, so that's my point. Yes, you can get free data. You can download free Landsat data, but it's not going to help you at the scale you want. It's great for government, though. It's great for researchers that want to say what went on across the entire state of Delaware this year. This is the same image zoomed out. So, yes, at that scale, you can see separate fields. You're not going to detect who was at work that day. You will be able to see across the region what happened at this time. Maybe there are images from this area where we're going to be able to see what did rainfall do to some of these crops this year. Maybe not at the scale they want, but it would be there for researchers that want to look what happened with the weather this year across the mid-Atlantic. Maybe it'd be useful for that. So it's useful to government agencies and monitoring land use and crops over the season. I will also tell you that unless you're trained in it, if you're working at the NRCS and you have ArcGIS, this data is probably easy to get. If not, you don't want to go looking for that. We're starting to get to the point, so ArcGIS has created ArcGIS Online, which a lot of people can use, and a lot of these universities and government agencies are starting to put information up there for you. I have some information on Maryland and Delaware. Maryland has a very useful website that can give you some of this data, and you can look through an area at some pretty good imagery. That NAIP imagery from 2013 to 2017 is available. They have color infrared. They also have LIDAR and elevation. This is an entire elevation map of the state of Maryland, which is accessible to you for free, and you can zoom in and look. That LIDAR data I had at the Princess Anne area is on here, and it's free, and you can look at it, and you can look at elevations that way. There is a new website. Salisbury University has Eastern Shore Regional GIS Center, who are supposed to serve the lower shore. They are trying to create an AgGIS website. The AgGIS website has elevation ag parcels, irrigated areas, ag ditches, zoning, stream buffers. They've actually mapped out all of the center pivots across here. You can turn on that layer and look at where center pivots are across this area. This is another free site. They also want to work with farmers to allow you to upload yield maps to it so you can overlap. Of course, we also have private companies doing some of this. But if, again, you're looking for free, here's your free, and it's not bad. But right now, this is for these lower 4 counties in Maryland. Delaware has First Map. It doesn't have all of this kind of information yet, but it does actually have some very interesting, it was fun to look through. They have historical imagery. So I was going through it and looking at what did Lewis look like, back in 1926, where were their fields, how has stuff changed? So that can be information if you're interested in history. Again, it's not going to help you monitor crops during the season. So it really does come back to drones as being one of the easier things. You can purchase satellite imagery, but if you want some accurate measurements and you want to scout crops, it is looking like drones are an affordable option outside of going out and taking that test and getting your license. All this imagery from drones can be taken whenever you want, not wherever you want, but whenever you want, and get an idea of monitoring during the season on your time scale and on the resolution you want. And for about $800 to $1,200 in most cases, you can get a very simple drone, and you don't need NDVI to go out there and look at what's going on in these fields. You can see that there's variability in the soybean field. You can see what's going on. This is our Warrenton station. You can see what's going on in these regions very easy without having fancier cameras. The fancy cameras help, but they're not necessarily what you need. So the UAVs, the camera types you can get with the UAV include a visual. A GoPro is pretty common, but if you buy a DJI that comes with a camera, it's a very nice camera. I'll show you some of the images I've taken. This is with a DJI camera. It's high quality. So the GoPros, they had some bend to them. They had some bowing. They weren't necessarily very nice. You could buy a multispectral camera. This camera costs $3,000. It's helpful to me, but I'm telling you, you don't need it yet. You really don't. These visual cameras tell you plenty. The thermal cameras are getting cheaper, but they don't necessarily have a cheaper option for me to use that tags it with GPS points for me to stitch them together later. But they are available, and there's one that came out that I put in a grant for. It cost $9,000, but it would be very useful to me in research. Again, I love this stuff for research. I don't think you need it. I think with a regular visual camera, you can see plenty, and the point, this thing goes slow. I like to put too many pictures in my presentations. It slows them down. Okay. Same image. Here's NDVI with my $3,000 camera, picking out NIR and red light, doing its calculation. We had nitrogen trials on this corn. So you can see higher biomass. You can see our plots going across here, but you didn't necessarily need it. Here's the same visual image of these two areas. Here's our higher nitrogen rate, here's our lower nitrogen rate. You can see it. Does NDVI pick it up in a little better detail often? Yes, it does. For me, as a researcher. But for you, you can see plenty with a visual camera. So what they're trying to sell right now on, we can measure health with a multispectral camera. Well, yeah, they can measure some very accurate things, but with a $1,200 drone, you can see plenty at 200 to 400 feet. You don't need to go out and buy this expensive stuff yet. I don't think it's ready to go in most cases for what you need it for. Because what are you going to do with that? That you aren't going to be able to do with that. You see that, you tell someone, walk out to that field and see what's going on. I know what's going on here because we did that on purpose. So coming back to this image, I talked to you about doing ground penetrating radar. If you're able to take imagery throughout the season, you're going to see where those soil differences are. This is an aerial image of this same field. This was mapped with an Order 1 survey where there's the aerial photo. See that soil type going across there? It's there. If you're out enough during the season, and we saw it this year, you can catch what's going on. You can look back later in the season and find out why things changed and why things went the direction that they did. So this higher biomass, and you know how crops are, every season's a little different, so you have to gather data over time. But in this year, we had enough rainfall that this crop did well, but not enough that this part of the drier soil, that soil with less clay in the subsurface, did well. So ground penetrating radar, Avaris, would be great for mapping soils, but you might, over time, if you get one of these cheaper drones and start flying your fields next year and flying for a couple years and get up enough, you're going to pick up on all this information. This was one of our research projects at the station. We were putting out inoculant later in the season on some soybean. Walking in the field, we got across there. My technician said, I think I see some differences. I think we actually found something. Well, I took the drone out, took it up in the air, and what we couldn't see walking the ground was very obvious that we had a soil type difference. Those are not square block treatments. So what this was able to provide us, and some other people that work with drones within the industry have been able to see, sometimes when we get back our plots and research now, we can actually pick out zones, and if we have a lower yield, we can find out it actually wasn't our treatment. It was something outside of our control. But you have to fly it. You have to gather the information, you have to act on it, and you have to use it. That's kind of sometimes where this disconnect is. If you're provided satellite imagery through a service and you don't use it to the end of the season, it didn't do you any good. If someone gives you an image of a field and there's something wrong with it, you don't want to look back in November and say something went wrong in July. If you see it in July, walk out and find out why and see if you can correct it for the next year. So that's our plan now. Now that I know this is here, we're going to go out and soil sample this fall and find out, is it something in the subsurface? Is it not holding enough water? Because I can't keep applying different treatments out here and not getting results because there's field variability I can't control. Do we need to center our plots in certain spots? So that's kind of how it will help us. Drone resolution can be a lot better. This is the image of that field at 300 feet. I can zoom in on it on the computer, and you can see that there's soybeans there. But if you want to hover 10 feet over that field, or you want to hover 5 feet over that field, you can. You use up some battery life, but you can fly over top of a field and you see something you think is suspicious, you can come right down over top of that and get a picture. You're not going to get that necessarily with satellite imagery. The nice thing about satellite imagery is it's going to come to you. You don't have to worry about it. But you still are going to have to act on it and walk out in the field. If you have a drone, you can go out there and get a lot closer. You can get a lot better detail of what's actually going on. The problem with larger fields, though, if you want to give an image of a larger field, comes down to stitching. So these are all single pictures of a field. You can get smaller fields. We can get our research fields. You might not necessarily get, this is Warrington Farm. We've got about 90 acres out there that we need to capture. See all these different lines and angles? That's thousands of photos that I have to stitch together. So once you get to larger fields, if you want to have one image, a satellite can get you one image of that field. A drone cannot get 90 acres in one image unless you're at some kind of angle, maybe. So now you have thousands of photos. I have over 1 gigabyte in raw data from one flight. And I have what would cost you about $8,000 in software. It only cost me $1,200 because they want educators to use it so it can get promoted. But if you tried to buy the software I'm using as a private company, they would charge you $8,000 to stitch these photos. And then the question is, do you need it? Is that satellite data that you're getting through Encirca or Climate Field View good enough to give you an image of the entire field that then you take your $1,200 drone out and fly over top of that corner and find out what was going on in the satellite image versus spending all of this money? So a nice thing about some of these images, I had a slide in here earlier about topo maps, is you guys ever heard of stereography? It's where you take two images that overlap, and that's how we drew topo maps. You see these multiple images from a UAV. Here's the tree line. Can you see all those dots? So we can use UAVs, because it's taking so many images that overlap, to measure elevations. Not as accurate as LIDAR, but that's why some people are starting to want to try to use UAVs in construction and industry to measure piles and measure holes and measure regions by hand. So there are other things you'll be able to do with it. It's not as accurate as LIDAR, but you can do it. So for me, in most cases, I think that NDVI is very helpful for research. Again, this is the Warrington Farm. You see these squares we have right here where we're trying to do dry land corn versus irrigated. We got to the end of the season. All the corn looks the same. It's all dried down. It's all brown. They go through the center of the plot, and they had a very good yield in that square. And then when we came back and looked at the image, we found out that there was a wet spot in the middle of that field. And just because I happened to fly it in August, we had the NDVI, and we could say, well, actually, that of that entire block, that was the best yielding part. So that's information for us to say, well, maybe there wasn't a treatment difference there, or maybe we removed that treatment. These are some different cover crop plots that we're doing with the NRCS, where we're doing different seeding rates of cover crops. So now we have an additional measurement that we can give to researchers, put into papers of biomass. So instead of just applying it, going out and doing like a square count or doing a measurement or using Canopio with a phone, now with one drone flight, I have this entire research plot, and I can use these NDVI measurements to say this was the relative biomass. It gives us another data point for ourselves to give information to people. Same thing with this. Last year we did different wheat seeding rates. So now instead of just going out and counting tillers and eyeballing the field, with one flight, I have in all of these plots, I have an NDVI measurement that gives me values and numbers that I can use to report how well we're doing. So NDVI, I think, is great for research. Visual images is, I think, all you really need for scouting at this time. So if you are thinking about buying a drone, and I know some people are hesitant, but if you've never flown one, the first time you take one up and get a look at that field, you'll recognize the value very quickly. First of all, here's some of the ones we have. I have an X over a fixed wing. Do not buy anything that has wings, period. Don't buy it. They don't have landing gear. They like to come down hard. They're pretty sturdy, but it's not something you want to fool with. You want all these things that are called quadcopters. They have rotors on them. So this is a 3DR, it's the American company, out of business. Here's a Chinese company, DJI. They produce high quality drones, UAVs, that are easy to use. Make sure it's a quadcopter. Make sure it has a camera. If you go on Amazon and you see a $300 drone, it probably doesn't connect to your cell phone very well. It probably doesn't have a very far range, and it might not have a good camera on it. You spend $1,000, you spend $1,500, you're getting a high quality drone. Make sure it has a camera. Make sure it connects to your phone so you can fly and see the images. If it's up in the air and you can't see the images coming back to your phone, it's useless to you. It's just a toy. Make sure it has a good range for your field side. Again, if you spend the money, if you spend $800, $1,000, $1,500, you're getting something that's going to be able to fly that 90-acre field. If you go buy one of those $150 drones, it might get 50 feet from you, lose signal, and it might even fly off. These companies, they want you to buy their drones. They don't want to get in trouble with the FAA. They have fail-safes on them. If their battery's dying, they're going to come home without even telling you. They're like, I'm coming home. They will come back to where they're supposed to land. If they lose signal with your controller, they will come back to home. I'm not saying over the next 20 years that one of these isn't going to fly off and there's not going to be a problem with it. But if you spend the money, you end up with something that's safe. They want to sell drones. They don't need these things flying off and leaving you behind. They will come back in most cases. I'm just telling you, because if you get on Amazon, you're like, oh man, look, this one's $200. Well, you're going to get what you pay for. They might be good starters to get used to it, but in most cases, these things are pretty easy to fly. So for remote sensing and crop monitoring, knowing the types of remote sensing is important. So you can understand, well, why are we talking about NIR? Why are we talking about far infrared and thermal and the visible spectrum? Why are we talking about green and blue? If you understand those, if someone's talking to you about a product or a camera or a drone and trying to sell you something, then you can be knowledgeable about what you actually need. Viewing data right now through online portals is easiest, and it's probably going to get even easier. Governments and states are probably going to realize the value of getting this information to you so you can use it for free. AgGIS and Maryland IMAP are good examples, but I think that more universities and governments are going to make this data available to us, and you can also pay for it from companies like Encircler and Climate Field View that's going to work with your entire operation. The skill level and cost will control how you use the data if you find it useful at all. If you really want to get good at some of this, you're going to have a higher skill level and have more training, which we might be able to offer in the future in working with things like ArcGIS Online, having some trainings of how you might use this or upload your own yield maps to those. You can do that. I have uploaded my own data to ArcGIS Online. If you want aerial imagery through the year, you got two pretty good options. You can go with the private companies that are providing you with satellite data, or you can buy a drone probably for a pretty similar cost. One you're going to have to do yourself, the other it's going to come right to you. So it's your decision. So we do have some outreach. When I worked at Maryland, and we'll update it for Delaware because this was February 2017, so with drones it's way out of date already. But we did have a fact sheet I wrote with James Atkins when I was at Maryland. We have a website. I keep it private because the university always changes their online portals. So I keep the drone stuff on my personal website. All the fact sheets will be there so they won't be lost. But information about which one you should buy. How do you get your license? What do you need to study for the license? Again, if you don't have your license to fly the drone, the FAA is not on every corner. They're not going to find you. But as a business, you have to have it. The test isn't hard to take. If you were to crash into somebody, you could end up getting fined. So it's up to you whether you fly one without a license or not. I have a license because I work for the university and I want to publish data, so I will do everything by the book. So most of the stuff we have up there is about drones, but as our precision ag program gets going, we'll add more stuff and more information.